Hello, everyone. Welcome to OpenInfra Live. This is a brand new series. It's brought to you by the Open Infrastructure Foundation. We are coming to you live every Thursday at 1400 UTC. The 1 hour long episodes are featuring production case studies, demos, conversations with industry experts about all the recent and latest and greatest hot topics, and updates from the global open infrastructure community. And if you would like to be featured in one of these episodes, then please throw your ideas into ideas.openinfra.live. So my name is Iliko Vancha. I'm with the Open Infrastructure Foundation, and I will be your host for today's show. So let me start with a quick reminder. These shows are not just live, but they are also interactive, so we need you to participate. This means that you can throw your thoughts and questions into the chat of any platform where you are following us, like YouTube, LinkedIn, or Facebook, and we will do our best to get to your questions at the end of the episode, where we have some time reserved for questions and also reflect to your thoughts and give us any feedback if you have some during your show. So make sure that you don't forget to participate and be part of our show today. And before we are deep diving into our topic for this episode, let me shout out to last week's one, because we are kind of going along those lines a tiny little bit. So last week we had industry experts Martin Casado, Bruce Davey, and Amar Padmanabhan joining Jonathan Bryce and Mark Collier to talk about how to bring connectivity and provide connectivity all around the globe, and what the challenges and opportunities are there, including talking about open source technologies such as Magma or ORAN, or, well, Open Radio Access Network, if you're not really a big fan of acronyms, and OpenStack. If you happen to miss last week's episode, not to worry, we do record all these, so you can go and check out all past episodes on our YouTube channel, and you can also get back to this one if you want to rewatch it later. So connectivity. We will not talk about connectivity today, but we will look into what happens when you do have it available. So, drum roll and all excitement, we will talk about edge, but not just the edge itself. So edge computing has been a really hot topic in the past, well, at least 3-4 years. And at least in my experience, it is still a bit of a confusing and challenging space because we are still only just scratching the surface. And when it comes to challenges, the whole thing starts with edge itself as a definition, because there is still no one definition that rules them all. So why that might be? If you look into edge computing use cases, there are a few ones which are running in production already, but the number of potential use cases are growing rapidly. And with the new use cases, they are also bringing in new industries. So while it started with telecommunication, now we have automotive, healthcare, industrial, agriculture, and really anything that you can imagine. And because of this, especially if you look into some of the ones at the end of the list, you wouldn't have really connected them to IT and technology just a few years, maybe even just a few months back, like agriculture, for instance. So this shows the diversity of use cases in edge computing. And with this diversity, there also comes diversity in requirements. So this means that when I say requirements, then you probably think of things like latency or security, bandwidth, remote management, and then bringing that to the next level, zero-touch management. But even these requirements that pop into most people's minds, they are just different enough for each use case that you can't really say that the edges in those use cases are the same and they have the same requirements, even if the words themselves match. So because of this, when you talk about edge, you cannot really assume that the other person has the same edge in mind as you do when you're talking to a new person in your company or a new group of people. So you always need to define your edge and give context, and then also listen to other people's perspectives, just to really make sure that everyone knows what you're talking about when you're talking about edge. And this was just the definition, and this was just focusing strictly on the edge. But edge, if you look at the word itself, it is the edge of something. So the edge is the device, the small or micro data center, but it's not alone. It's not just in itself. It is always connected to a regional data center, a central data center, and in some use cases to other edges. And this results in a spider web of massively distributed systems. So this kind of brings back something that we knew already, like distributed systems, but elevates it to a whole new level with the massive scale that many of the edge computing use cases have. And because of that, we have some new challenges in the areas of testing, deployment, management, and orchestration. And we also have some challenges and requirements like interoperability, which we sort of solved already, but they are back into the spotlight. As you can see, there are challenges, conundrums, some confusions and misconceptions in this space. So how do we untangle the edge? This is something that the OpenInfra Edge Computing Group is looking into. So in the next segment today, with my co-speaker, Gergely Csatari from Nokia, who is also my co-conspirator in the Edge Computing Group, we will talk about the group, what it is, what it does. With that, we can just go to the next slide to jump quickly into the introduction part. So this group is a top-level working group that is supported by the Open Infrastructure Foundation. And this top-level ability also means that we are really not exclusive to any technology when it comes to edge, but we are looking into these massively distributed systems and infrastructure to build your edge with, and your end-to-end edge solution, and not just the edge or far edge or very, very far edge itself. So our group is looking into solutions and software components in the open source ecosystem for the infrastructure as a service layer. And to understand better the requirements, we are collecting all these use cases from all the industry segments and more that I mentioned already, really trying to understand the requirements of the edge computing space and what demands it puts on infrastructure. And with the use cases and requirements that we collected already, we are building reference architecture models and sharing that with the broad industry, not just the open source ecosystem, but really everyone who's interested and needs information. We are collaborating with adjacent groups and communities, and also trying to bring these infrastructure models to life, implement them with projects and services from open source projects like OpenStack and Kubernetes, really trying to figure out how you can create the best infrastructure for your workloads. You can find out more about the group on our wiki page. We also published 2 white papers that talks about our view on edge and also our work in the reference architecture space and all the relevant testing and other activities. And coming to that, I will give the word now to Gergely, and he will guide you through the architectures and some of our activities.
Thank you, Ildikó. And let's go to the next slide to see the architectures, what we are discussing in the Edge Computing Group. If you can, oh, thank you very much. So in this group, we realized that there is no one-size-fits-all solution for edge computing, but still we we recognized some pattern in how you can architect your edge computing infrastructures, and we created these two, let's say, ideal architecture models, which are the centralized control plane and the distributed control plane. I will discuss them a bit later. But as Ildikó described previously, every use case basically requires a different edge cloud infrastructure, because the different workloads have different requirements, and the different use cases require different behavior from the cloud in case of, for example, connectivity loss, or in case of any unwanted events. Also, we are looking into infrastructures which are growing organically. So we are looking into scalable infrastructure of infrastructures, because edge is basically a system which is built from cloud infrastructure. So it's somehow distributed architecture of distributed architectures. We think that connectivity should be in our focus, and we are distinguishing the behavior of these edge cloud infrastructures based on how do they behave when connectivity of the edge cloud instance is lost to the other parts of the infrastructure. And in case of the centralized control plane, we have in one location all the control functions of the infrastructure, and the edge data centers are running only those components which are needed to run the workloads, but all control functions are running in one central data center. This solution is not capable to manage the life cycle of workloads in case of a connectivity loss between the edge data centers and the central data centers. But on the other side, there is no need for synchronization of any metadata between the edge and the central data centers, because the centralized control plane ensures that all requires data to manage the whole infrastructure is consistent and in one place. On the other side, the distributed control plane runs all the control plane functions in every edge data center, which means that there is an overhead in the control plane in every data centers. But the benefit of this architecture is in case of a connectivity loss, the data center is still able to run all the management functions and manage all the lifecycle management events of the workload. So in this sense, these edge data centers are autonomous, and they can run the whole functionality of an edge data center on their own. The problem here is that to provide a consistent view on the state of the whole system, there is a need for some kind of a central management and data consolidation functionality, and some kind of a federation which provides a single point of access to the whole infrastructure. We know that these are very idealistic architectures. This is why we call them reference architectures, and most of the solutions are somehow mixing these. So some components are implementing the centralized control plane approach, and some other components are implementing the distributed control plane. For example, if we are looking for examples around the OpenStack, OO implements the centralized control plane model more or less, while StarlingX, what will be covered later in this session, is implementing the distributed control plane approach of the reference architectures. If you would like to read more about these reference architectures, and if you would like to see one example implementation of these on paper using different OpenStack components, then please look the URL which is shared in the slide, and there you can see a detailed comparison between these two architectures. Okay, let's move to the next slide, where I will discuss a bit about other things what we are doing in the edge computing group. So basically, what we think the role of the group is to connect the ecosystem. So we will think this group as a, let's say, an open collaboration forum for all groups and persons who are interested about edge. And in the edge computing group sessions, everybody can bring their topic, and we are happy to discuss and share our experiences from our company or industry. And we saw very interesting discussions where representatives from different industries were sharing the same problems, basically. Currently, what we are trying to do is to untangle the challenges of the edge computing ecosystem, which is what we plan to be a set of blog posts, what we would draft together, and we figure out the topics together, and currently we have the topics around the no one size fits all definition, so the exact issue what I just described in the previous slide, and we are planning some discussions and blog posts around how 5G and edge are not the same thing, and also we are trying to cover network transport for edge, and also we are looking for other topics. So this is, as I mentioned, like an open discussion forum where we are discovering problems and solutions for edge, and we try to somehow distill the conclusions into these blog posts. We are very excited to work on the first blog post. We are currently collecting these blog post ideas in an Etherpad and working on the separate blog posts on different Etherpads. What we hope from these is that we are accelerating the collaboration between the different groups around edge, and we can like consolidate the different ideas and different projects around edge by opening up a discussion forum and somehow providing a public opinion sharing platform about problems and solutions of edge. So if you are interested in all of this, then please join us. We are meeting on every Monday, 6 a.m. PDT. You can see the wiki pages of the Edge Computing Group. In the main wiki page, you can see all the resources and all the information about the group. And we have one mailing list, and of course, we are maintaining an IRC channel, which is Edge Computing Group on the Freenode channel. I don't know, Ildiko, if did I miss anything?
No, I think it was a great overview. Thanks, Gergely. And I would like
Thank
to
you.
just kind of emphasize on participation and collaboration. So as Gergely said, please join us on the weekly meetings or our mailing list and bring your use cases, architecture models, your feedback if you agree with the ones that we have already, or you have one that doesn't fit into any of the models that we have. And when it comes to participation, let me remind you here that this is an interactive session. So if you could join us live today, please throw your thoughts and questions into the chat so we can get to them and answer at the end of this episode. And with that, we are ready for our next segment today, which will be about StarlingX. This is a open source cloud platform, fine-tuned and optimized for edge and IoT use cases. And StarlingX is implementing the distributed control plane model. So now you can see how this actually works and how it looks like in practice. And we have invited contributors from the community to introduce the project to you and guide you through the latest features of the 5.0 release that the community is just putting out as we speak, and give you a bit of a sneak peek into the project roadmap after 5.0. So we have Greg Waynes and Matt Peters from Wind River and Min-Yuan Chi from Intel. So with that, Matt, if you're ready, the floor is yours.
All right. Thank you very much, Ildiko. So hello, everyone. My name is Matt Peters, and I'm a software architect with Wind River and a contributing member for StarlingX. So I'd like to start us off today, if I can, with just an overview of StarlingX. I know not everyone may be aware of everything that StarlingX is providing and how it fits into the into the OpenInfra Foundation. So StarlingX itself is an open source integration project under the foundation. It offers a fully integrated software stack for a collection of open source projects, but mostly targeting the Kubernetes platform with the support for containerized workloads and support for virtual machines, which is enabled through the deployment of OpenStack. So it's specifically tailored to the edge use case, and we do target a lot of the requirements for that edge use case. So with that, we really have an emphasis on reliability, so a focus on 5 nines or better, and we do that across all of the platform infrastructure management, monitoring, all the lifecycle operations. So as you'll see later in the presentation, I'll talk a little bit about how we do that across the distributed cloud and some of the orchestration of those operations. We have a specific emphasis on scalability. So this actually goes both directions. We have a look at how we can reduce the footprint for the StarlingX deployment to be able to fit on lower cost edge server hardware. But we also have the ability to scale up to a multi-node system and even a distributed system. So we really have an emphasis trying to make sure that the distributed control plane that we have has the smallest footprint possible while still meeting all the requirements for these edge use cases and those applications. Because we do deploy at the edge, we do have an emphasis on security. So all the communications between any of the centralized components and the distributed systems are all encrypted. We have full certificate management across the system, enabling both the lifecycle management of those certificates, but also just the awareness that those are present and be able to manage those from an end user. So we are a platform, so we do open it up to being able to integrate with other PKI solutions. And then finally, but not least, is the ultra low latency. So we do have a specific profile that's tailored to real-time applications. And we really want to make sure that we meet the demands for that. And specifically, you'll see that in some of the 5G use cases for something like the virtual RAN, where they have strict requirements for some of both the timing infrastructure as well as the real-time scheduling. StarlingX itself can deploy both standalone, so that would be a standalone cluster, or it can be deployed as a set of distributed clusters. And I'll take you through more detail of that later. So next up, I'd like to go over some of the use cases we're seeing in the industry. And as you can see, there's a full landscape of different industries contributing both applications and services to the overall solution for the edge. And what we're seeing is most of these are being enabled by the introduction of 5G, but it's not strictly geared toward that. But a lot of it is being enabled from that, just from the flexibility you get and the availability you get for network connectivity. So the NFV edge infrastructure is really where the 5G landscape fits in. And we're seeing the key infrastructure for that, at least in early deployments on the vRAN side. But really, this is expanding rapidly, and we're seeing adoption across many industries of being able to support that, and many tier 1 providers as well. On the autonomous devices, we see definitely a demand for and an expectation from users and industries for autonomous vehicles, autonomous devices such as drones, both for industrial and for military use cases. So there's definitely an expectation and a trend in the industry to deploy and manage those systems at the edge. And I think there's been lots of talk also around some of the immersive experiences. So having the connectivity and the low latency at the edge really brings in some of the compute power that you need to be able to drive things like augmented reality and virtual reality. And those immersive experiences are really geared towards some of the entertainment, commerce, and industrial use cases. And finally, but not least, there's definitely been an explosion in the industrial IoT and analytics, and we're seeing a huge demand in both scale on the number of devices being connected and the bandwidth requirements for those particular solutions. There's a vast number of devices that are collecting data, and the need and the desire to monitor and manage all of that data. So both from a feedback to be able to get real-time operations and interactions, but also to monitor the operations and health of those systems. So I'd like to take you through a couple use cases more specifically, and we'll do a little bit more of a deep dive on these. So the robotics use case is definitely one that we're seeing in the manufacturing space, and the key driver here is really on two things. One is being able to bring connectivity to these devices. So most of the existing ones are isolated or standalone control systems for the robots, and not necessarily connected into an overall operations and management. So the desire really is there toward bringing that in and being able to get the visibility into these systems. They do have, in some cases, they do have existing infrastructure where they have hardwired connections to these systems, and it's very costly for them. So they have to, if they want to reconfigure the robots into a different assembly, or they have new components that they're bringing online that they need to monitor, can be extremely costly. So with the flexibility of introducing 5G and some of the wireless capabilities and secure capabilities for bringing the edge, we do enable the capabilities for being able to reconfigure at a much lower cost. So giving the flexibility and the agility to be able to reconfigure without needing to deploy new physical cabling across those systems. And further to that, there's the vast amounts of data that are being generated by these systems can be coordinated and managed at the edge, where there's much lower latency to be able to do real-time analysis and operations across those systems. So as you move more and more of the intelligence to the edge, you're able to bring up the intelligence of those components and be able to monitor the health of those systems. So really getting into more of a predictive analytics to look for failures, to analyze the operations for performance, as well as being able to collaborate between some of the other systems within the overall control path. So you're really looking at a more of a converged control plane where all of them are working together rather than independently and monitoring independently. The next one use case I'd like to talk about is the smart buildings, or the connected building. So with the introduction of the smart technologies into these systems, really we're seeing an expansion across all of the different components. So both the energy management, the communications, security, the infrastructure management, all of these needing to be managed and coordinated across the entire building. And with the size of these systems, they are generating vast amounts of data. And to be able to provide the best experience for their residents or the specific service that they're providing, then they're really looking at being able to bring in some intelligence to that monitoring system and just the overall operations. So again, it has very similar requirements to some of the other use cases we're seeing for the intelligent edge, where you have real-time analysis, you need low latency communication between the different building control systems, and they need to bring in some artificial intelligence to be able to make real-time decisions about what's happening with the different components. So if you making fine-tuning adjustments to some of the energy consumption, you can save energy across the entire building, being able to coordinate events during security situations, and really looking to bring some additional awareness into the overall building and coordination across them. So those are kind of the two key use cases that we're seeing an explosion of edge adoption, and really the bringing forward the advancement of the 5G use case. So what I'd like to do now is, before we go into some of the feature details of what StarlingX has most recently developed and what we have on our roadmap, I'd like to go over one of the key capabilities of StarlingX, which is the distributed cloud. And this allows us to deploy the distributed control plane. So I'd like to take you through that architecture, how we manage that across a distributed architecture, and really how we manage that from an operations perspective. So the distributed cloud today is comprised of a central system component, and that central system component is typically deployed at a regional data center. And subtending from that across a geo-distributed architecture is the subclouds. So we refer to these edge systems as managed subclouds, and they're independent control planes and worker functions to be able to manage those workloads at any geographic location. So specifically, the communication path between that central control plane and the edge is a L3 routed path, and that just allows us to have a larger gap between the central control plane and those distributed systems. Since each operates autonomously at the edge, we're able to deploy those with having individual components communicating and managing the synchronization between the central system controller and the subclouds from an operations and management perspective. And we don't necessarily need to be able to bring the data infrastructure across that for some of the management. So it's not an extension of the control plane, which means that we can tolerate longer outages, disruptions for the network, or even longer latencies. So if it really allows us to have some flexibility at the distance at which we can deploy those geographically dispersed systems, and also the scale at which we can operate. So if you look at the centralized components, there's a number of things called out, but most of it is around the orchestration and the lifecycle management of the entire distributed cloud. So we want to be able to bring the ability to manage these systems, since they are discrete systems across the different network components. So we have the ability to do software management, which includes software updates and software upgrades. So that's a live software upgrade and live software updates across the entire distributed cloud. And that is orchestrated across the entire system. So both managing the local software within the system controllers, but also the software across all of the remote subclouds. So we're able to apply those patches for the software updates, restart any services that are required, and coordinate that activity across a multi-node function. So if it's a standalone simplex system, then typically they're deployed in a cluster of them to be able to continue to provide geographic supportability. Or if it's in a redundant pair or multi-components, then we're able to coordinate the activity of applying those updates across all the multiple nodes to prevent outages. So in the case of each of the subclouds, we also have the ability to group them into different subtexts to be able to have individual components and individual subclouds coordinated. So not just at an individual subcloud level for each node, but able to do groups across each of those systems. So that means that you can coordinate to prevent outages if you have overlapping regions for some of the 5G network, as an example. Then you can make sure that the upgrade path and the disruption to services for software updates will coordinate across those different systems, so that you don't lose the wireless connectivity for those regions. So in order to manage the system, if we go to the next slide, I'd like to talk about the deployment. So StarlingX implements the ability to deploy those remote systems using Redfish, and specifically we use a bootstrap image that allows us to bring up the remote system from a powered off state, so basically bare metal, bringing it all the way up to running a fully managed Kubernetes platform or OpenStack platform to be able to run your workloads. So from the starting point of initial media install, which is the direct from a unified installation media or an ISO, we're able to bring up the centralized system, and then we push that same media out to all the individual subclouds through the virtual media from Redfish. And this allows us to distribute the software without actually physically being on site, and to also coordinate the update activities and bootstrap of those systems when they're being deployed. So if you look at this particular architecture, the initial bootstrap of the system is done with Ansible. So we're able to deploy those systems first with the virtual media to install the initial software. Then we bootstrap the system using a remote playbook for Ansible to deploy the Kubernetes platform. And then on top of that, we deploy the workloads. So if, for example, OpenStack is required, we will deploy OpenStack as an application, which would make it ready for deploying virtualized workloads. So out of the box, we get the fully distributed management and control plane for the distributed cloud. And that's all done through a common set of media for doing the initial installation. Further to that, to support the containerized workloads, we have central image registry. So this is a container registry, and that really allows us to do a full air gap installation. So this means that we can do a deployment from that initial offline media, distribute that out to all the subclouds, and do a deployment across the entire distributed infrastructure without going back to a public internet site or something like that, so that we can have a fully contained and secure environment. And this is especially useful for both tier 1 operators as well as industrial use cases where you have critical infrastructure that you want to have a closed system. Go to the next slide. I'll talk about how we manage this from an operations perspective. So as you can imagine, having each independent site brings some additional challenges. So we achieve that by having a central single point of management across the distributed cloud. So this is support of both the day 1 and day 2 operations. So the central system controllers are responsible for the aggregation of both the state and alarms and events that are coming in from those remote systems. So this allows us to look at the state of it across the individual subclouds, but also at an aggregated view so that you can monitor the overall health of your system. And this is the same interface where we do deployments for software updates and software upgrades and the overall orchestration for those. So we have the ability to distribute the new software and new software updates across the entire distributed cloud from that central location. We also support the ability to drill down into an individual site. So if you're needing to look at individual health of a subcloud, if you're debugging a particular issue, or you just want to do operations that are localized to that particular system, then we also support the ability to directly connect to that subcloud and manage it locally. So that's the overall distributed cloud architecture and management. And now I'd like to hand it off to Ming-Wan to go through some of a set of the features for StarlingX that we introduced in the release 5.0. So both Ming-Wan, myself, and Greg will present a few of these features, and then we'll wrap it up with what's coming in StarlingX 6.0. Over to you, Ming-Wan.
Yeah, thank you, Matt. Yeah, hi, my name is Mingyuan Qi, and I'm with Intel and also a TSC member of StarlingX community. I will introduce 3 new features of incoming 5.0 release. The Rook Ceph one, Rook is a storage operator set that manages multiple storage backends. So Rook Ceph is one of its operator. In 5.0, we introduced the Rook Ceph for containerized Ceph solution. As a user, you can now install StarlingX Rook Ceph application and deploy multiple Ceph clusters with CRDs. All Ceph daemons are containers and orchestrated by Kubernetes. If a user have an existing 4.0 system, after 5.0 upgrade, it's optional to migrate the Ceph cluster from native Ceph 1 to Rook Ceph. We have a complete guide for helping people to do so. But it's not mandatory. You can still keep the Ceph cluster running as it was. As well, if it's a 5.0 fresh deployment, both native Ceph and the Rook Ceph are supported. They can be deployed together or using just one. For Rook Ceph, there's an advantage that the OSDs are not stick to controller nodes or storage nodes anymore. The hard disks can be placed in any nodes. With Rook Ceph, the storage management in the StarlingX 5 is more flexible, so it's another choice to enable Ceph cluster. Next slide, please. The Edge Worker feature, it's an experimental feature in 5.0 that comes from our users from industrial domain. The idea here is to add nodes which have Ubuntu OS installed. These nodes may not meet the minimum hardware requirements of a standard worker node, but they are still eligible to become a StarlingX node. The new functionality is called Edge Worker. The Edge Worker nodes will be displayed along with the other nodes on the same host list. The Edge Worker node is not only a StarlingX node, but it's also a Kubernetes node, which means the StarlingX application is available for applying to the services to Edge Worker nodes, including Rook Ceph. The Edge Worker feature is now in phase 1. Next slide, please. Yeah, SDO or FDO. This feature is called Secure Device on Board. It's a technology to provide a fast and more secure way to onboard any devices to cloud or on-premise platforms. Now SDO is adopted by a FIDO Device on Board, FDO, standard, which is announced by FIDO Alliance. So it's may change the name to FDO. So let me introduce the SDO first. When an IoT device is manufactured with SDO, it gets an ownership voucher to identify itself. If a user powers on it and connects to the internet, it will connect to the rendezvous server with its ownership voucher to get itself authenticated. Then the rendezvous server will automatically direct the IoT device to the target device management platform for provisioning in the secure tunnel. So in 5.0, we integrated SDO rendezvous service as an application. This main component of SDO enables StarlingX the ability to authenticate the IoT devices and onboard them to any platform, including StarlingX itself. Okay, for the rest of the features, I'll turn over to Greg.
All right, thanks, Nguyen. Yeah, so the next feature I was going to talk about was the integration of Vault for secret management. So this is the open source Vault project. HashiCorp is the main contributor there. Basically, the integration, the StarlingX integration of this involves, packaging the Vault Helm chart into our Armada system application format, as well as handling the complexities of setting up the storage backend required for Vault, managing encryption keys, and managing sealing and unsealing operations, and that's all stuff that you have to deal with when configuring and installing Vault on Kubernetes. So Vault is actually provides a ton of different capabilities. We've in StarlingX have initially validated it primarily as a secret manager, but I imagine in future releases we'll validate it for other capabilities. Like, for example, Vault has a really good certificate authority that would be useful to be able to run on StarlingX clusters. But as a secret manager, like I said, we validated the capabilities there. Vault does have a pretty extensive secret management capability, providing encrypted storage, pretty flexible policy-based access control. There's actually a variety of different secret types of secret storage engines depending on particular use cases, and also a variety of authentication methods. Although the default authentication method that we actually document in StarlingX is to use Kubernetes service accounts for authentication. But the basic idea here is that to have have Vault pre-integrated on StarlingX, because for end user applications that currently use Vault, which is a fairly popular service, it enables much easier reporting to StarlingX for them. All right, next slide. The next thing, another integration activity that we did in StarlingX R5 was to integrate the open source Portieris project. Now, this is a project that's primarily contributions from IBM, but it is open source. Portieris provides basically an admission controller to enforce image security policies, such that any images that are getting pulled for Kubernetes pods basically can be checked against security policies to do things like only allow images pulled from trusted registries, as well as if the registry that the image is being pulled from has a notary server, you can actually also do image signature validation from the trust data that's in the notary server. One thing to note here is that as part of this integration activity of Portieris, we actually upstreamed into the Portieris project itself a couple of enhancements. First one was we actually made it work generically for any Docker for generic Docker registries. It initially only worked for IBM Docker registries. And then we also optionally added capability to support the certificates used for the the admission controller as to be managed by Cert Manager. Next slide. So we added SMP v3 support in R5. We had previously we already currently supported SMP v2c, and just as a reminder, the SMP functionality for StarlingX is actually only focused on fault management data. So any alarms that are raised by StarlingX components as FM alarms or logs, they get sent out as SMP traps. And then SMP also provides access to StarlingX's FM's active and historical alarm tables. So the active being, the actively set alarms, where historically you can see the sequencing of sets and clears of alarms and logs. So V3 was basically introduced for improved authentication and privacy over V2C, which is just a simple community strings. And actually, just a thing to note is that the introduction of SMP v3, we actually used it as an opportunity to rework the integration that we had of our SMP solution, which is based on the open source NetSMP. We actually reworked it to be a containerized solution. We used to have it on the host, and this is just a general direction, that long-term direction that we want to go with StarlingX, is to containerize components of StarlingX. So moving it into a container made sense there. And it also helped for configurability. Like you can configure just with simple Helm chart overrides in the exact format that SMP uses. You don't have to do any we didn't have to do any wrapping of configuration commands with StarlingX REST APIs. And that's it. Go to the next slide. I think it's to Matt.
All right, thanks, Greg. The next feature I'd like to go over is a new framework that was added to StarlingX for allowing the applications to obtain the synchronization state, or the PTP, which is the precision time protocol state, from the host. So the onboard NICs that have the timing coming into them are synchronizing the clock to the host. But in many cases, the application needs to be able to have knowledge of what that state is and whether it's healthy. So being able to make decisions around the health of the PTP clock synchronization, and to be able to coordinate some of the activities across different nodes based on that as well. So this framework introduces both a registration function so that applications can come up and register for specific events, as well as a tracking function to be able to track the state against the different PTP clock sources. So in this case, the slave state and the slave clock source would be sent to the application based on the notification framework. So to integrate with those containerized application, a new reference sidecar is introduced, and that implements the notification API. And some of the standardization around this is being done in the Open RAN community. So this is a software community that's defining the specifications for integrating some of the infrastructure management for the RAN use cases. On the next feature I'd like to introduce from the 5.0 release was support for the NVIDIA GPU operator. And this was key for enabling a number of different use cases, but specifically around being able to support augmented reality and digital image processing. So the new operator allows for applications to be deployed and consume GPU resources, and it controls the full life cycle. So this is both the introduction and management of the NVIDIA drivers, the introduction for the device plugin into Kubernetes for managing the allocations to the pods, and the overall runtime to be able to support the interactions and the deployment of those services that are running CUDA to be able to interact with these devices. So, NVIDIA is definitely one of the early adopters of this framework and introduced this.
So it looks like that we have a quick technical glitch. So I wonder if we have Greg still on to hop quickly over to 6.0.
Yeah, I can. I think we just had one slide left and then open it up for questions and answers. I think the last slide was really just to talk about what's next. So we just finished PTG meetings in StarlingX, and R6 and upcoming features was a discussion item there. You can see the timelines. This would deliver end of the year. And as far as features, these are all to be confirmed, but definitely the key items. One of the key items is, I think as probably indicated previously, StarlingX is a top-to-bottom solution on dedicated physical servers. So we provide the kernel, and the recent changes with CentOS means that we need to move from CentOS to something else. We've picked Debian, And that is going to be a lot of work for us. And then the remaining key features, we're going to do some up-versioning of kind of Kubernetes components. We're going to continue scaling distributed cloud, continue doing some simplification and auto renewal of certificate management. And one thing I want to point out at the bottom is that the Armada subsystem that we use from Airship has been deprecated, so we need to find a replacement for that. We'll certainly be looking at what Airship chose. But other than that, that's those are some of the key features that are being thought of for StarlingX R6.
Great. Thank you all. I do get a little bit of echo, so if we can fix that, that would be great. But until that point, thanks to all of our speakers today. I think we just delivered an amazing package of content, both about the Edge Computing Group as well as StarlingX, what the platform can do, and highlights of the latest key features for Edge. There's always a large focus on security, and you could see that there are features also like the precision time protocol for more mission critical workloads as well. So from the chat on the different platforms, I could see that people really liked the highlights of the use cases and the session so far. And I did see one question that we are also seeing on other channels as well and get it a lot, which is StarlingX running in production? So to answer that, I would like to give the floor to Matt.
Thanks. So the answer simply is yes, it is in production. We have key deployments with Verizon for their 5G infrastructure, as well as T-Systems. So they are both using StarlingX and a commercialized version of StarlingX, I should say, through Wind River, and being able to provide for their 5G vRAN use case as well as the industrial use cases.
Amazing. I'm really excited to hear this, and it kind of also shows how the telecommunication sector is the pioneer in edge computing, as they are the ones who are providing that connectivity on the first place, so making it possible to really take the cloud out of the data centers, out to the edge, and really provide a compute and storage resources for critical workloads there, and new types of workloads. So it is really exciting to hear that StarlingX is running at those two large operators in America and Europe. And I'm excited to see where else the platform will be deployed. And with that, we are at the top of the hour. So I sadly have to say that this was all that we could fit into this hour for you, but not to worry, because we will be back with a next live episode next Thursday. Remember, 1400 UTC. So those of you who joined today, you successfully solved the little challenge of what time is it in my time zone. So please encourage your friends and colleagues as well to solve the exercise and join us next week. So what will we be talking about? Next week's episode will actually be part of a series within the series. It is called Large Scale OpenStack, and it is brought to you by the Large Scale SIG, or Special Interest Group, within the OpenStack community. And this group is looking into challenges and solutions and techniques in terms of how to run an open source cloud platform on a massive scale. So we are talking about hundreds of thousands and millions of cores in production powered by OpenStack. So next week's episode will be about upgrades. And even if you are not running OpenStack, I'm pretty sure that the headaches of upgrades has already been part of your life with OpenStack, with another tool or project. So I would really encourage you to join next week, because we have speakers from a couple of operators to share their techniques and also create a lively discussion. So to mention examples, we will have Blizzard Entertainment, Bloomberg, OVH, WaxHost, Workday, and CERN, because we cannot have a session like this without CERN. So it is really exciting. Remember, Thursday, 1400 UTC. And if you would not be able to join, you can always check out the recording on our YouTube channel after. And one other reminder, or well, two actually, try to join live so you can participate in the session and the discussion itself. And the other one is that if you have some topics for OpenInfra Live in general, then please submit your ideas on ideas.openinfra.live. And with that, that was all that we could bring to you today from all over the globe. We had speakers from North America, Europe, and China today. So really, it is a global event, and I'm hoping to see you next week back here. Thank you.